This screencast is one in a series on reactor calculations, and the title is The Batch Reactor Numerical Solutions. And the content is the mass balance for the batch reactor and some methods how to calculate the concentration as a function of time by means of the MATLAB function ODE45 and the time to reach a certain concentration with the MATLAB function quad. We're going to have example 1. We calculate the concentration as a function of the time for a single reaction. Example 2, where we calculate the time to reach a certain concentration. And example 3, where we calculate the concentrations at a function of time where we have multiple reactions. Reactor calculations for the batch reactor involve solving the following differential equation. The reaction rate equals dc dt. And this is what remains from the general mass balance equation input plus production equals output plus accumulation. The general integral providing the solution is the following, where the variables have been separated, so we have concentration on one side and time on the other side, and the appropriate boundary conditions have been inserted. Numerically, we can either use these equations to solve for c as a function of time or t as a function of concentrations. ODE45 is a MATLAB function that is used to integrate a set of differential equations, and they can be coupled so that the differential equation describing the change with time for Ca can be a function of other concentrations of substances in the system. The output from ODE45 is, first of all, a plot of the concentration as a function of time for the interval specified, but it's also a matrix with all the corresponding values for time and concentrations. And if the differential equations are defined in an M file, the syntax is the following. The other method I'm going to demonstrate is quad. A quad evaluates integrals on the following form. The output from quad is simply one value of t. And if the integral is defined in an M file, the syntax is the following. Let's do some examples. Let A and B react in a batch reactor according to A yields B, and the reaction rate is R equals K times Ca. And calculate numerically concentration of A and the concentration of B from time equals 0 to time equals 4 if the rate coefficient is 0.5 and the initial concentrations are 3 and 0.2 respectively. If we combine the mass balance shown before with the rate equation, the design equations become dc dt equals negative K times Ca, and the other one is dc dt equals K times, and here's an error, it should be K times Ca. One thing we must do before we use MATLAB is to determine how should we translate the variables in our mathematical notation to MATLAB variables. First of all, we must recognize that the concentrations Ca and Cb form a vector C. And we'll also say that the differential equations will form a vector dc. So that Ca equals C1, the first element in the vector C, Cb is C2. And for the differentials, dc1 is dca dt, and dc2 is dcb dt. And the rate coefficient k is simply denoted k. So let's go to MATLAB and solve this problem. Here we have a clean MATLAB window. The first thing we'll do is to create an M file. And the M file will be saved in my folder demos. And I will call this M file example 1. And now I'm going to write my function. The function to be integrated, the output from it will be a vector dc, and dc is defined in example 1, and it has two arguments, the time and the vector of concentrations. We then define the rate coefficient k, which is k equals 0.5. We also need to predefine that the vector of differentials dc is a column vector. Now it's time to define the differential equations. dc1 equals minus k times c1, while the second differential, dC2, the differential of B, is K times C1. We now save it and go to the command window. And the first thing we do is to set the path to the folder demos. And there we got it. And it's now time to apply the function OD45. So we write OD45. Then we need to tell MATLAB where it can find the function to be integrated. We give the time intervals 0 to 4 and give the initial values of A and of B. And we get the following nice graph where the blue curve represents the concentration of A and the green curve represents the concentration of B. And we see that Ca decreases from 3 down to about 4. And to summarize, we had a reaction A yields B with R equals K times Ca, and numerically we calculated the concentrations of Ca and Cb from time equals 0 to time equals 4, and the result is shown to the right. We will now take an example where we apply quad. A and B reacts in a batch reactor according to A yields B with the usual rate equation. Calculate numerically the time it takes to reach a concentration of A equals 0.406 if K equals 0.5 and the initial concentration of A is 3. And again, the design equation is dCA dt equals minus K times Ca. What we should do is to evaluate the integral time equals function of C from the initial concentration to the final concentration. And in this case, the integral from 3 to 0.406, and the function is the inverse of the rate equation dC over minus K times Ca. Translated into MATLAB terms, we say that Ca equals C and K equals K. So let's go to MATLAB. The first thing we do is to create an M file. And that M file should be saved in the folder demos, and I will call that example 2. And example 2 contains a function where we calculate dt, and it's defined in example 2, and the only argument is a concentration C. We must define the K as 0.5, and then we say that dt equals minus 1 divided by K times C. You have to be very careful and very specific whether it's a scalar or a vector quantity. And now is the time to apply the MATLAB function quad. So we write quad example 2. We give the lower time interval, we give the lower concentration and the upper concentration. So we make the integration from concentration 3 to concentration 0.406, and we get 4. And that is the time it takes for the concentration to go from 3 to 0.406. So in summary, we had a reaction, A yields B, we had a certain value of K, and we calculate how long it would take to go from concentration of 3 to a concentration of 0.406. And quad told us it takes 4. The third example is more complicated. Here we have 4 components, A, B, C, and D, and react in a batch reactor according to A yields B in reaction R1, B yields C in reaction R2, C yields B in reaction R3, and finally A plus B yields D in reaction 4. The kinetic equations are the following. R1 is first order with respect to concentration of A, reaction 2 is first order with respect to concentration of B, Reaction 3 is first order with respect to concentration of C, and reaction 4 is second order with respect to concentrations of A and B. Calculate all concentrations after 4 time units for the initial concentration of A equals 1. The general mass balance equation is dc dt equals R. So the design equations become the following. dCA dt equals the sum of the rate equations by which A is consumed in reaction 1 and reaction 4. The change in concentration, dCB dt, is the sum of the rate equations for the reactions in which B react, and so on. And now we should solve this system of differential equations by means of ODE 45. And we should use the notation that CA equals C1, that CB equals C2, that CC equals C3, and CD equals C4. Here we have a nice and fresh command window. And the first thing we're going to do is to save it under an appropriate name in the demos folder. The appropriate name is example 3. We now define a function to be integrated. The output will be dCs, the final name will be example 3, and the arguments will be time and concentration. The first thing is to define the various rate coefficients. K1, K2, K3, and K4. Thereafter, we predefine the dimensions of the vector dc. Then it's time to define the differentials. dc1 equals minus k1 times c1 minus k4 times c1 times c2. The differential for B is it's produced in reaction 1, it disappears in reaction 2, it's produced in reaction 3, and it's also consumed in reaction 4. The differential for C is dC equals, it's produced in reaction 2 and it's consumed in reaction 3. And finally, D is only produced in reaction 4. So we now save this and we go to the command window. And the command window we use ODE 45. We write the appropriate file name. We want to make the integration from 0 to 4. And the initial values of the concentrations are 1 and 0 for B, 0 for C, and 0 for D. And here we get the output, the concentrations of A, B, C, and D. And in summary, we had a complex reaction system with A, B, C, and D and 4 reactions. And we calculated all the concentrations after 4 units of time for the case where we had an initial concentration of A of 1, and we got the following results. The content of this screencast was the mass balance for the batch reactor, how to use ODE 45 and quad. And then we had 3 examples where we calculated concentration in a single reaction system, calculated time to reach a certain concentration, and finally we made a calculation for a multi-reaction system involving 4 components.